coming to Cornell is like coming home for me. My grandfather was a professor here, and growing up, Ithaca was the United States for me. I grew up not in the United States, and we would come here and visit Ithaca. And so just being here is great. So thank you for the opportunity, and it'll be nice to go back this evening and see some old friends and places. So today, I'd like us to explore a topic that I've spent, now it became close to a decade looking into, or maybe over a decade. I fell into this by mistake. I didn't intend to study hurricanes and tropical cyclones, but it just took off, and what was meant to be a single paper became a decade. And so what I would like us to try and consider is the answer to two questions that to me in 2006 seemed so obvious that I didn't even feel like answering them. But the more I learned, the less obvious the answers became. First is, how has North Atlantic hurricane activity changed and why? And secondly, what do we expect for the coming decades? The reason that this seemed so obvious to me 10 years ago was tropical cyclones, hurricanes, they're tropical phenomena. And so the planet has warmed. And so it was entirely obvious to me that tropical phenomena should become stronger and more prevalent. Katrina had just happened, Rita, Wilma. We'd gone through a very, very severe hurricane season. And so I just said, well, this is obvious. We're seeing an increase. Why is everybody looking at it? Well, what we've come to learn is that the situation is much more subtle than that. The answers are more complex. So one of the things that brought hurricanes to me personally, I've been fortunate all my life up to 2012 to have never experienced a hurricane in person. In 2012, my daughter was 5 weeks old, and the eye of Sandy passed over our house. We spent a week without power. With a newborn and the cold front that followed Sandy. And so we would pack up, we had gas water heaters, so we'd take showers in the morning to warm up and then go to my job that had emergency power, and we'd all sit there as a family among the other families. Having no power was nothing compared to what other families had to go through. There was a number of fatalities, people lost everything. And this is a story that repeats itself every time we have a landfalling storm. To a greater or lesser degree. Puerto Rico is still digging itself out of Maria. It's not in the news that much anymore, but there's still no power to first order in Puerto Rico. So these phenomena have very dramatic effects when they happen. And so I think, hopefully, even in Ithaca, actually, there was once a hurricane that flooded Ithaca. So pretty far from land. And even as far as the Midwest of the United States, if you go up in as far north as Minnesota, there are some flood events that are related to the rainfall from extratropically transitioning tropical storms. So very impactful. Now, what does the US landfalling hurricane record look like? So every year, the National Hurricane Center and its predecessors will try and write down how many major hurricanes. And major is defined based on the Safer-Simpson intensity scale, which is keyed in on the maximum winds of the storm at any given point in time. And the convention is that a major hurricane is a hurricane whose winds exceed 50 meters a second, or about 100 knots. And this is the number making landfall in the United States, the continental United States, from 1851 to 2016. And what you should see is that most years don't have a major hurricane hitting the US, fortunately. But there are a number of years that do. And even in the late 1800s and early 1900s, we had some years that had 3 major hurricanes hitting the United States. And so there's a lot of variability. And if you try and model this statistically, you wouldn't really distinguish it from what we know as a Poisson process, a memoryless process, something that doesn't know what happened before. But what we have is a few years that are really prominent. 2004 and 2005, which are the two spikes at the end, show a large number of major hurricanes. 2005 was the year of Katrina, was the year of Rita, was the year of Wilma. And those years came at a time when we were really becoming attuned to the potential impacts of global warming. These storms had big impacts, and it really keyed in our perception of the impacts of hurricanes, perhaps from global warming. But then that was followed by what was a number of years without major, defined by category 3, 4, 5 hurricanes hitting the US. So this period went on and on and on and on, and eventually it went on so long that we said this is starting to become statistically unlikely to have between 2006 and eventually 2016 with no major hurricanes hitting the US. Both Sandy and Irene, which had very large impacts, were not considered major because of their wind speeds. And so in the scientific community, we started talking about the major hurricane drought. There's a number of papers that are still in press right now trying to explain the existence of the major hurricane drought. And as those papers were written, we started to understand, have explanations for what was going on. Came 2017, which you may remember is only last year. And in 2017, we had Harvey, which was a major hurricane, and not only that, parked itself off the coast of Texas with its landward winds aimed right at Houston. Over 3 days, led to some catastrophic flooding over Houston. We had Irma, which had some pretty big impacts, but it could have been much worse. Had Irma's track been 30 miles to the west of where it was, had it been over the ocean, its impacts would have been much worse because you would have had strong winds pushing water into Tampa Bay, and you could have had much more flooding. So it was bad, but it wasn't as bad as it could have been. And then we had Maria. Maria, the wind, the rain, were both incredibly impactful on a number of islands, most notably, I think, for us in Puerto Rico. And many months from that, we're still trying to dig ourselves out there. And so as the papers trying to explain the hurricane drought were waiting to be published, the hurricane drought went away. And this little bit is sort of an explanation, is trying to illustrate the fact that this is an area where the scientific community is trying to react to what is happening on the ground. We have 2004, 2005, big active hurricane seasons. We're trying to understand what's going on, impact of global warming. Then we have 10 years without hurricanes. We try to understand why that's going on, and then we get 2017. So there's going to be a lot of explanations as to why 2017 was what it was. But the key is to be less reactive and sort of be more systematic about it. Let's try and build up hurricane and climate understanding. What can we say about hurricanes and climate, right? The other thing is the Atlantic isn't the only place where we get hurricanes. Hurricanes is a region-specific name for a general phenomenon. Phenomenon is known as the tropical cyclone. It is a large, spinning, cyclonic system that draws its energy from evaporating warm surface waters, takes that warm water vapor, condenses it in the atmosphere as it rises, and that heats the atmosphere in the middle, and it further strengthens the storm. In the Atlantic and the East Pacific, these phenomena are known as hurricanes. That derives from the Taino word, for their sort of god of mischief and destruction. And once an East Pacific hurricane crosses the date line and goes into the West Pacific, it becomes a typhoon. So in the Northwest Pacific, they're known as typhoons. It's the same thing, same feedback, same phenomenon. They have regionally specific character, but that's not related to the name. Anything in the Indian Ocean or in the Southwest Pacific is known as a cyclone, but it's all the same phenomenon, right? It's just regional names. There have been a number of very notable cyclones. The 1970 Bola cyclone in East Pakistan, what was then East Pakistan, which is now Bangladesh, killed over 500,000 people. And The political consequences of that were quite large. Does anyone know what happened after 1970 cyclone? No? So it's not known as East Pakistan anymore. It's known as Bangladesh. And part of the reason was that the response of the central government in West Pakistan was viewed as so abysmal that East Pakistan decided to go their own way. And so a country broke up, precipitated by this impact of this large cyclone. So you can have political instability, poorly designed or structured societies that become very vulnerable to these big events. 500,000 people dead is a lot. In 1975, Typhoon Nina killed almost 250,000 people in China. This was a rain-fed event. It moved inland in China, dumped a lot of rain, and then that flood came down river and led to a series of catastrophic dam failures as you went down. So it was the storm triggering sort of failures in the infrastructure that led to the death. So it's not the storm directly, it's what we build around the storm and the vulnerability we create for ourselves. In 2015, we had very interesting, first ever recorded major hurricanes hitting Yemen. And these are the type of things that subsequently we have come to think that global warming may be influencing. So it's a global phenomenon. I'm going to focus more on the Atlantic. So as I said before, tropical cyclones, you have a warm ocean that fuels the hurricanes. You have a feedback, so self-reinforcing processes where the strong winds will give you evaporation. That evaporation will load moisture into the atmosphere. That moisture acts as a fuel. In the atmosphere, moisture is energy. That's its main role, and then that energy is released as rain, as precipitation, but the rain is just a consequence of the energy. The main transaction that goes on is that energy is moved upwards and then converted into heat energy and then eventually into electromagnetic energy and then goes to space, right? The transactional cost is that some places get wet. The tropical cyclone, typhoon, and hurricane are the same phenomenon, different location, and they spin cyclonically, which means, let's see if I can do this for you, it means counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, so that the equatorward winds are westerly, that is from the west. So there you have a primer on tropical cyclones. There's a lot more. Here is a map of where tropical cyclones have formed over the period, I believe it's 1980 to 2010. Each little dot is a location where a tropical cyclone was identified as having formed, and the shaded map behind it is the surface temperature of the ocean on average. The red colors, the bright orange colors, that indicates warm ocean. What you should notice, I hope, is that there's two geographic clusterings that happen to storms. One is that they tend to form over the warmest waters. You see that they form over the yellows and the reds and the oranges? Right, it's clear there. But not everywhere. You notice what's going on along the equator? There's an absence of storms forming there, right? The storms have rotation. Part of that rotation is drawn from the rotation of our planet. And as the stretching happens, it goes into the rotation of the storm, kind of like the ice skater, if you will. So they can't really form on the equator because the equator isn't rotating relative to the axis of our planet. So it's perpendicular, it's parallel to it. So there's no storms forming on the equator. But what we come to know is that warm water is sufficient, it's necessary but not sufficient for tropical cyclones. There's other factors that are involved. If any of you are from sort of the Gulf Coast, Florida, the Mid-Atlantic, you probably pay attention to the hurricane forecast as the storm is out there, and you might have heard the forecasters talk about shear, wind shear. It's a difference of wind, speed, and direction with altitude in the atmosphere. And shear, the shearing of winds, will act to rip a storm apart. It'll take the top part of the storm and move it away from the bottom part of the storm, and you won't be able to have the storm cycle energy and water through it as efficiently, and it'll tend to break it apart. So for a storm to exist, you want low shear. You want a moist middle troposphere, middle of the atmosphere, to be moist so that as the air is rising, it doesn't draw in dry air and kill itself off. And there's a few other factors that you want, right? One of them is a cold upper atmosphere. You want a warm surface and a cold upper atmosphere. That is the ideal condition for a storm. And that's going to be a recurring theme, so try and remember that one. How you get to this, and I'm going to put an equation here, don't get scared about it. The most important thing to remember of it is how I break it down there. It says potential intensity is equal to efficiency times a fuel. There's a theory, one of the most fundamental theories, the only really fundamental theory we have about hurricanes is Kerr-Emanuel's potential intensity theory. You can derive it from thermodynamics and knowing some dynamics of the atmosphere. So if you keep taking atmospheric dynamics classes, you'll be able to do it just fine, but you're not going to do it now. And the way it's interpreted is that the tropical cyclone is thought of as a Carnot heat engine. If any of you are engineers, any of you work on cars, you maybe have heard about this. And the idea between a Carnot heat engine is that you're doing work on the system, and there's two main things that control how much you're getting out of this Carnot heat engine. One is the fuel, how much fuel you're putting into the engine, and the other one is the efficiency, how efficiently you can turn that fuel into work. And much like in the Carnot heat engine, so the amount of fuel is controlled by those K terms there, and those K terms tell you about how much energy there is near the surface, how much you can evaporate energy. And that's, again, as I said, moisture is energy. And so that term there on the right is your fuel, how much energy is available, and that increases with a warming surface. So the more warming you have, the more you can evaporate. The second term, which is on the left, is the difference between the surface temperature and the temperature of the upper atmosphere. That's what the TO is, divided by the temperature of the upper atmosphere. There, the temperature of the atmosphere comes in two places. One, in the denominator, so that the smaller it is, the bigger that term is. And once as a negative in the numerator. So again, the bigger it is, the smaller it is, the bigger that number is. That is an efficiency term. So it has an analog when you do the Carnot heat engine, or maybe your experience may be that if you run your car in the winter, you tend to be more efficient because the environment is colder, and you run your car in the same conditions in the summer because the environment is warmer, you're less efficient. I don't know if you've noticed that, but it's something you may notice. So in general, a storm will like to have more fuel and more efficiency. Both the fuel and efficiency increase as you warm the surface. However, the efficiency goes down as you warm the upper atmosphere, or it goes up as you cool the upper atmosphere. Okay? So let's keep that in mind. We want a warm surface in a cold upper atmosphere. This is the plot that really got me into hurricanes. The figure updated from 2007, from an original in 2005 by Kerr-Emanuel. When I saw this, it floored me. What it shows is, in the green line, a record of Atlantic hurricane activity since the mid-50s, all the way to what then was the early 2000s. You see it going up and down, and sort of trailing up, right? And then in blue, it shows the temperature of the ocean in the tropical Atlantic. Again, going up and down, going up and down, up and down, and it's trailing up. And those two lines are right on top of each other. You see all the wiggles kind of match? In geophysical data, this is a variance explained of 0.75. In geophysical data, when everything is connected to everything else, we never see variance explained of 0.75. When you see that, you say, oh my goodness, this is some correlation that maybe tells us there's some causality there. And if what's going on is the warming of the tropics is giving us more hurricane activity, we've only seen a little bit of the warming we are going to get. What's going to happen when we go forward? That was pretty scary. And so you start thinking about that. What I'd like to tell you is that this story, the narrative is very compelling, but I think it's incorrect, it's oversimplified, and it goes back to the story I said, that it's not just the surface, it's the surface minus the upper atmosphere. And this only looks at the surface. So just to illustrate this, this is a figure my colleagues, Brian Soden, Kyle Swanson, and I put together, so to reframe the question. And What it shows on the top is another version, another way to recreate that plot of Carey manuals, and it shows on black the hurricane activity in the Atlantic. In red, that is the temperature of the Atlantic where hurricanes form. And you should see a very strong relationship. It's a very nice relationship, very statistically significant. However, there's another ocean temperature-based index shown down there in blue that shows exactly the same statistical relationship as just surface temperature in the Atlantic. And what that is relative sea surface temperature. The difference in sea surface temperature between the Atlantic and the rest of the tropics. So what the top question is asking is saying, how warm is the Atlantic? The bottom panel is asking, how much warmer than the rest of the oceans is the Atlantic? It's a slightly different question, particularly when you're thinking about global warming, where to first approximation, the tide is rising all ships, right, for temperature. There's a difference. From the point of view of correlation and inferred causation, there's the same correlation between the two. So from the historical record, there's no reason to pick the blue one or the red one. And so what? Big deal. Do you have two statistical relationships? Well, the big deal is when you start projecting these forward. If you start saying, what do we think temperature is going to look like over the 21st century? The top bar shows what the world may look like if the true dynamical relationship is between the total temperature in the Atlantic and hurricane activity. We're looking at a future that looks nothing like the past. Unprecedented hurricane activity changes, right, at least in the historical record, very large changes. Where the lower bound in our expectations is comparable to 2005, so the most active year in a hurricane. The lower panel shows that if the true relationship is between the patterns of temperature change, between how much the Atlantic warms relative to the rest of the tropics, then you're looking at a future that looks somewhat like the past, where you go through active and inactive phases, but really we're not bouncing out into a whole new reality. And it's important to distinguish between these two, because adaptation measures would really depend on these. So how do we go and ask this question better? I told you that from this point of view of correlation and implied causation or inferred causation over 1950 to, say, 2010, the two statistical relationships look the same. However, that was from 1950. We have data going further back. Since 1878, the U.S. Signal Corps, which is the predecessor of the National Weather Service, has been tasked by Congress for recording all hurricanes that they can find. And so you can go and download a data set. It's known as HURDAT, the Hurricane Database. It has a list of the hurricanes since 1851, but really since 1878, they're more reliable. And so what you can do is say, how have they changed? And you can put them in context of global mean temperature. So the top plot shows a time series of the globally average temperature. It's standardized so that the variations in each one of the lines are equivalent so that you can see them all on the same scale. And you see that the planet has warmed. I'm hope that you know that, you realize that we know that. There's some uncertainty exactly by how much it's warmed, but we are very, very, very confident the planet has warmed since the 19th century. We're also very, very confident that a large part of that warming is due to increasing greenhouse gases. Okay? The second line shows tropical Atlantic sea surface temperatures, the temperatures of the Atlantic. You see that there's a lot more variability from decade to decade, but generally there's a clear warming trend. You can show with a certain degree of confidence that a lot of that warming is also due to greenhouse gases. Although because you're only looking at a region and you can redistribute temperature around the world, you're going to have a lot more variability. Right? The only way to change the temperature of the whole planet is by letting more energy into the planet or letting it out. But if you want to change the temperature of just one place, you can move energy from somewhere else to there, so you can vary more. The third line, the blue line, that's if you go down, download this data set that I mentioned, the HURDAT, and you count the number of hurricanes each year, and you filter it so you only retain the low frequency data. And so this is the number of recorded hurricanes every few years. And you see that there is a clear trend. There's an increase in the number of recorded hurricanes in the Atlantic. It's a very clear increase. It's very statistically significant by any way you want to estimate significance. So the number of recorded hurricanes in the Atlantic has increased. And it shows a very strong resemblance to temperatures in the Atlantic. Is that evidence, strong evidence for an increase in the number of hurricanes? The number of hurricanes we recorded isn't necessarily the number of hurricanes that there were. That's one thing to keep in mind, right? So right now, it's 2018, we have satellites, a constellation of satellites up there. We have airplanes. We have trained meteorologists looking at all this data. We have reconstructions of all sorts of types. We can see hurricanes in ways that in 1878 we couldn't. In 1878, if you wanted to see a hurricane, it had to hit you, or hit someone you knew, or it had to hit a ship at sea, right? That was the only way. There was no satellites, there was no planes, there was no way of recording this. So what? Well, the impact of that can be seen in that lower left panel, which on the top part of it shows the tracks of hurricanes, where they tend to happen in the Atlantic. And you see that they tend to happen starting in sort of the western part of the Atlantic. And each of the three heat maps you see there are typical ship tracks, a density of ship tracks in three epochs. One, the top left one, or the top right one, is in the pre-Panama Canal era. In the pre-Panama Canal era, there was almost no ship traffic, very little density of ship traffic in the western Atlantic. It's almost like the negative space of where hurricanes happen. It wasn't that the ships were trying to avoid the hurricanes, it's just that there was no real good economic reason to sail into the Caribbean, at least if you wanted to get to Asia or get, because you had to go around Africa or South America. The post-Panama Canal and the post-World War II era show that there's an increase in ship traffic, although it's not full coverage. It's not like what we get from satellites that are going on all over the place. So what my colleague Tom Knutson and I did is we ran a simulation. We said, we know what the hurricanes from the satellite are. We know what the ship tracks from the past are. What happens if we blow the hurricanes from the modern era over the ship tracks from the past? How many slip through the cracks? And you can calculate this for every year, and what that allows you to do is adjust the number of hurricanes for known changes in observing practices. And that gives you that red line. The red line is an adjusted hurricane data, homogenized hurricane data. This is the hurricanes that were observed, plus those hurricanes that we can't exclude from having happened. They may have happened, they may have not, but you cannot say they didn't happen. When you include those hurricanes, all of a sudden the trend goes away. There's no more trend, meaning that the recorded trend in hurricanes can be entirely attributed to our changes in observing practices. That's very different from global mean temperature. We've gone over and over and over global mean temperature. We are sure as we can be, that changes in observing practices aren't behind the increase in global mean temperature. Global mean temperature has increased for real. Atlantic hurricanes, it's not clear that they've increased. Which is kind of good news, because when you look at US landfalling hurricanes, there's also no trend. And all of a sudden, if hurricanes had increased, but US landfalling hurricanes hadn't increased, we have to explain why is there an increase in one and not in the other. It becomes a tougher problem. And then in the bottom, I show Atlantic relative sea surface temperature, and if you believe me, I could show it, but just trust me, that the pattern of ocean temperature is a much better predictor of the corrected hurricane data. So the last 100 years don't really serve as a way to assess what's going on. So what can we do? Well, another tool that we have available is a global dynamical model. I don't know if you've discussed this in the seminars before, but a global dynamical model it's related to your weather forecast model. All it is a mathematical representation of the equations that control the atmosphere, ocean, sea ice, and land. And these equations, we understand them. The problem is they're too complicated to solve. The same way that you would solve, you can solve the equation in physics for throwing a ball up and watching it go in the parabolic arc, but the atmosphere and the ocean are too complicated. We can't solve them by hand. We can't solve them in closed form. What we can do is we can put them inside computers and solve them in an approximate fashion. And so that's what these global models are. we can run them in a number of ways, but these are the fundamental tools that we use to try and predict, at least project the future. We can tell them how much CO2 may be changing, other factors. And one of the issues about these models is that you have to break up the world into little tiles, and in each tile, make a set of calculations. You have to make millions and millions of calculations, so the more tiles and more pixels you have, the more expensive they become. And even though we're using some of the most expensive and more sophisticated supercomputers of the world, we're limited in how much we can actually do. And until recently, the tiles, the pixels that we could use, were limited to be a scale of about 200 by 200 kilometers, so 150 by 150 miles. Is that it? Or 120 by 120 miles. Some small amount of miles, but not that small. And so just to illustrate that, this is Hurricane Rita, one of the largest hurricanes ever in the Atlantic. And this orange grid in there is a 2 by 2 degree grid. So the typical scale of models. And what you can see is that you have the hurricane eye, the eye wall, and part of an outer rain band, all within one grid cell. But the model would only have one number to describe that whole place. And so these low resolution models cannot represent hurricanes well. So the size of these grids is limited by computer, so maybe we can't use them. However, we know about the large scale factors that control hurricanes. Remember I mentioned that we want to know about wind shear? Well, these models may not be able to represent hurricanes, but they can tell us what the wind shear is. Or maybe they can tell us what the potential intensity is, this upper bound on hurricane intensity that depends on the upper temperature of the atmosphere and the surface temperature. And so we can say, all right, models, what do you think this large-scale factor, how is it going to change in the 21st century? This was a calculation that my colleague Brian Soden and I did. And the story behind it is he's trained as an atmospheric scientist. I was trained as an oceanographer. We were working together. And we did some calculations on something, and we needed potential intensity calculated. And we knew that when you warm the planet, storms got more intense, so potential intensity should increase. And we know the warming happens, so the top is the average across a bunch of models of what surface temperature does, and it warms everywhere. And we expect the potential intensity to increase anywhere. And I told Brian, Brian, you calculate potential intensity change. And a couple of weeks later, he calls me back. He's like, man, I can't do it. I'm busy. And so then I call him back. I say, okay, I'll do it. And I do it, and I find, oh my goodness, I can't do this right because I keep finding areas where potential intensity is decreasing. And I know that when you warm the planet, potential intensity increases. How did I know it? Well, it was just sort of conventional wisdom, right? And I had received this conventional wisdom. And I was embarrassed because I couldn't do a basic task. So I called Brian. I'm like, I know, Brian, you don't have any time. Could you please do this calculation yourself? And so he says, all right. And he says, and then he comes back and says, I can't do it. And we're going back and forth and back and forth. And finally, we're having a drink together. And I'm like, Brian, I gotta confess to you, man. I'm unable to do it. It's not that I don't have the time. It's that I do it, I calculate, I get it wrong. I get these big patches of decrease. And he said, you too? Right? And we were sitting there, and both of us were convinced that we were wrong because our results were not meeting conventional wisdom. But in fact, that conventional wisdom was wrong. In a way, this is not as grand, but it's similar to the ozone hole. For the longest time, it was hidden because we assumed that there wouldn't be such large negative values. So we calculated this, and we found, oh my gosh, over half the tropics, potential intensity decrease. Is that what you see, those blue spots there? Then why does potential intensity decrease? And here we're going to get to this relative sea surface temperature. Contoured on top of that, with dashed contours, meaning places that warm less than the tropical mean, and solid traces, meaning places that warm more than the tropical mean, is the pattern of surface temperature change. It's just taking that top plot and subtracting the tropical average. And what you should see is pretty much all the places that are blue and green, where you have potential intensity decrease, have a warming that is less than the tropical mean. And all the places that warm less than more than the tropical mean have increases in potential intensity. This is where the idea of relative SST comes from, relative sea surface temperature. We see this pattern. Why is it there? Well, potential intensity cares about two things, the temperature of the surface and temperature of the upper atmosphere. The temperature of the upper atmosphere is not set locally. The upper atmosphere's temperature is actually set across the whole entire tropics. And so if you want to know what the temperature of the upper atmosphere is, look at the temperature across the tropics. And so when we are saying subtract the temperature of the Atlantic from the temperature across the tropics, it's a shorthand way of saying look at how the temperature of the surface of the Atlantic differs from the temperature of the upper atmosphere, right? And that tells you what potential intensity does. Now so that's sort of looking at the large-scale environment of cyclones, but we can actually look at, more recently, there's some advances in modeling that allow us to look more directly at tropical cyclones. And a few of the results that have come out is that if you want to look at the next few decades, changes in radiative forcing, that is the amount of greenhouse gases in the atmosphere, how much aerosols there is, all of those are going to be important players. But so is internal variability. The atmosphere-ocean system is a chaotic system. Even if no human had interfered with it, it would wiggle. You would have El Nino events and La Nina events. You would have weather. You would have ocean weather. And all of that would make things wiggle. And we think that the impact of those wiggles on hurricanes, at least over the next few decades, is going to be comparable to, if not larger than, the impact from greenhouse gases. That doesn't mean that there is no impact from greenhouse gases, just that there's something else going on top of it that sometimes will act to mask the impact of greenhouse gases, and sometimes will act to amplify the impact of greenhouse gases. The greenhouse gas signal will emerge, will become clear towards the end of the 21st century. Doesn't mean it's not going to be there while we're on our way to the end of the 21st century. It's just that it's going to be hard to see. We are facing some threats that are potentially quite meaningful, but they're going to be hard to tell in a very clear fashion. And for the next few decades, non-greenhouse gas forcing aerosols, soot and dust in the air, not spray cans, and internal variations are going to be key. So how do we know this? Well, I said that climate models are too coarse to look at high resolution, to look at something so high space scale as hurricanes. So what do? We do is we bite the bullet and we take our low resolution climate models to tell us about the large scale environment. That's illustrated there by that ball with the sea surface temperatures. Then we section off a smaller part of the planet and we put a higher resolution model where you have many more tiles per area, but you're solving it over a smaller area, and those represent hurricanes. And then we add another layer on top of that to even higher resolution to get to the intensity of hurricanes. And so that is one method by which you can go and take large-scale information and what we call downscale it, bring it to a higher resolution. There's pitfalls in it. There's ways it can go wrong. But we and a number of other centers around the world think that we've figured out some way to do it in a relatively meaningful fashion. And so one of the results of this is this. This is what we think the range of plausible outcomes from one study for what hurricanes and tropical storms will do in the Atlantic. The bars are the aggregate solution, so the likeliest outcome in some way, although it's not necessarily a very likely outcome relative to all the other outcomes. And the dots are a range of plausible outcomes that could happen. And so what you should be able to see is that the likeliest outcomes are for decreases in tropical storms in Category 1, so the weakest storms, perhaps also for the more moderate storms, but when you go to the Category 4s and 5s, the strongest storms, the ones that are most impactful, there's the projection for a potential increase. Now, that's not a guaranteed increase. The range of plausible outcomes go from about a negative 90% to a plus 250%, so there's a lot of uncertainty in that statement. But what this reflects is a combined effect of two things. We think that hurricanes are likely to become less frequent, but they're also likely to become more intense. And so if you want to worry about the frequency of the most intense storms, that is the product of the overall frequency and the intensity, or is a function of the product of those two. And so if you have one going down and the other one going up, you could have the weakest storms losing frequency and the strongest storms gaining frequency. But it's also because it's a product of two things that are going in opposite directions, it'll give you a great deal of uncertainty. So you see that big spread there. Now, the spread between minus 100 and minus 200, plus 200 is pretty big. But we had a number of centers do this. And so this is now focus on the horizontal axis, which goes from minus 100% to plus 100%. These are a collection of studies from around the world. Teams in Italy, teams in Japan, teams across the United States, in the European Union, the Bengtson study. And what they are is a bunch of different estimates about what could happen to hurricanes at the end of the 21st century. The range is anywhere from minus 90% to plus 70%. This is overall hurricane frequency. It's a lot of uncertainty, big range, although it seems to have, really no plausible scenario is really knocked out of this. So maybe we don't know anything. Well, it turns out we know a lot. What we know, so the difference across all these studies could be due that we're using different methodologies, that we're using different, we have different ways of analyzing the data. Another possibility is that we have different predictions for what the large scale at the end of the 21st century will be. And so the hypothesis we had, and that's tested in the vertical axis, is that what is going on is that each center is using a different pattern of sea surface temperature. And so we plot there on the vertical axis is the prediction based only upon relative sea surface temperature, the difference between sea surface temperature in the Atlantic and the tropics as a whole. And what you should see is that a lot of the spread across all these studies around the world is captured by that very, very simple observation. Does the Atlantic warm more than the rest of the tropics? Then hurricane activity increases. Do you think the Atlantic will warm less than the rest of the tropics? Then hurricane activity will decrease. So although we don't have a very good answer as to whether it'll increase or decrease, now we know what the crucial question to answer in order to get to that is. We need to know the pattern of ocean temperature changes. It's not enough to know that the planet is going to warm. If you want to know what hurricanes are going to do, you need to know whether the Atlantic is going to warm more or less than the tropical mean. And so it tends to focus the question. We need to know more about clouds. We need to know more about winds. We can then put this back into this plot. Remember, I was using this as a motivation. And we can put all the dynamical modeling studies as little green symbols at the end. And what you should see there is that the models, those encapsulate our theoretical understanding. It's a very complex theory, but it's a collection of what our theory is. And the dynamical model projections, our theory is inconsistent with a world in which absolute warming of the Atlantic controls hurricanes, but it is entirely consistent with a world where patterns of temperature change control hurricanes. So the aggregate of evidence using each little leg of evidence is somewhat tenuous, really supports the idea that it's the patterns of temperature change, not the overall warming, that matter. Now, more recently even, we now have global climate models, the type of climate models that are used to do global warming simulations that start representing hurricanes. So we no longer have to do this layering of one model on top of the other on top of the other. Here's an example. The tracks of observed hurricanes are on the bottom, and this model is on the top. And visually, they look similar. You can see some differences if you really key in on them. But believe me, this is probably the best simulation of hurricanes from a global climate model ever. And we can ask that model what it thinks major hurricanes are going to do in response to global warming at the end of the 21st century. And this particular model, which isn't a layering of models on top of the others, says that everywhere on the planet at the end of the 21st century, there should be more major hurricanes than there are now. So anywhere that you have major hurricanes now, you should have more of them, according to this model. Now, this is a unique model. It's the only one in the world right now that has these characteristics. Much like we saw spread across other models in their projections of the future, it would be nice if other models existed so that you could test against them. Now, I was talking about basin-wide hurricane activity, how many hurricanes in the Atlantic, as if that was the relevant measure to us. I think history, recent history, tells us that it isn't. In 1991, I'm guessing it's before most of you were born, there was what was probably the most inactive hurricane season in the Atlantic. There was, I believe, 3 named storms. There was 1 major hurricane. Or is it 3 or 4 named storms? It's 1 major hurricane, 3 hurricanes and 4 major storms, something like that. And so it would have been one of these worlds where I say there's basin-wide activity is very low. Except one of those hurricanes, the first one of the season, the only major one, was Hurricane Andrew. Hurricane Andrew formed in the eastern Atlantic, made its way across, intensified over the Bahamas, and slammed into Miami, causing all sorts of destruction. So if we had used this heuristic of we want to look at major hurricane activity, basin-wide activity to understand the threat of hurricanes to us, we would have missed the boat here. So other than later Katrina, this was one of the biggest loss makers. And if it were to happen today, after there's been all this construction in Miami, all this wealth put on the coast, it would be one of those events that would really have the reinsurance and insurance markets reeling. So the key here is that basin-wide activity isn't necessarily the key. And in fact, what we should do is focus on what we think matters for hurricanes. So I've spent a lot of time talking about hurricane frequency, hurricane intensity in an overall sense, and how we may not know what they do in response to global warming. However, there are other things for which we have much easier predictions, where it's not the pattern of warming that matters. All you have to know is that the planet is warming in order to know the sign of the response. The magnitude of the response will depend on details, but the sign of the response is determined. One of the issues is a warmer atmosphere can hold more water. You've seen this effect if you've ever held a cold glass of water or a cold glass of beer outside in a hot, humid day. It picks up dew on the outside. Or in winter, especially here, you will blow on your glass and you'll see the fog, right? This is that difference in the amount of water that cold and warm air can hold. That's the Clausius-Clapeyron relationship. As we warm the planet, the atmosphere can hold more moisture. If storms don't change, which right now we don't know how storms are going to change, so the central estimate is that they won't change. So unless we have strong evidence that they're going to decrease, for you decreases in this direction, right? A warmer atmosphere for the same storm will give you more rain. And the rate is about 7% per degree Celsius, or 7% by every 9/5 of a degree Fahrenheit, right? The other bit, and this is something that is observable, I do it in my students in the lab, you can see it with your own eyes, is that a warmer ocean expands and increases in mass because you have melting of land ice, and the expansion is from the temperature. So these are really well-established things you can see with your own eyes. As we warm the planet, sea level is going to rise. The other big impact of storms, other than rain, is storm surge. The same storm acting on higher sea level will give you bigger storm surge impact. We are very confident that sea level is going to continue to rise. So even if storms don't change, their impacts will become sort of more pronounced. Recently, 3 independent studies after Harvey occurred took a look at what the probability of rain like Harvey with and without the global warming we've had since the beginning of the 20th century would have been. And these 3 independent studies came to the same pretty much conclusion within their error bars, that Harvey increased the that global warming increased the severity of the rain that led to flooding in Houston, and that global warming, this is a converse statement of what I've said, increased the probability of rain as intense as we had during Harvey. It doesn't mean that it caused Harvey. It doesn't mean that it caused Harvey to stall. It just means that once you have a storm that is stalling and formed and pointing its hose at Houston, if it's on a warmer ocean and on a warmer atmosphere, it will drop more rain, right? Yeah, Harvey dropped 50 centimeters of rain. What's that? It's like 50 centimeters. It's a lot of rain. Big flooding. Now, it's not the only factor that contributed to the reign of Harvey. There's other factors, and you have to look at them all in aggregate, but this is one. It's isolating one factor. It's not dismissing the others. The other piece I mentioned is sea level. Sea level has risen, is rising, and will continue to rise. Even if we freeze greenhouse gas concentrations at their present levels, sea level will continue to rise. That means reducing emissions, right? In order to freeze concentrations, you have to reduce emissions, right? So even if we somehow froze concentrations, sea level would rise. We know sea level is rising, and we know why sea level is rising. This is one of my favorite figures. I wasn't involved in this in any way except for wishing it happened, and it did. We have 3 different estimates for sea level. Well, 4. The black line is a satellite-based estimate of the height of the Earth from a radar. So you have a satellite going around the planet, pointing a radar down, and measures how far the surface of the ocean is from that satellite. You know the orbit, you can figure out how high the ocean is. And it started in the early 90s, and you can see that black line rising over time. It wiggles up and down. Some of those have to do with El Nino. It's interesting. So El Nino, you tend to put a lot more water on land, and so that makes sea level drop. In La Nina, you tend to put a lot less water on land, and that makes sea level rise. It's kind of neat. But then the long-term trend is due to 2 factors, and that's the red and the blue line. The red is what we call steric sea level. That's a measure of the density of water. And that's determined by the salt content and the temperature of water. And for this factor, it's the temperature that matters most. This was measured by little robotic instruments that we have out there. About 3,000 floats that float around the ocean. They live at 2,000 meters depth, about 1.5 miles down. And then they pop up every 5 to 10 days, measuring the temperature a whole 2,000 meters up, and then they send that to a satellite. So every 5 to 10 days, over 3,000 points on our planet, we have measured the temperature, and we can see in that red line that the density of the ocean has been decreasing. It means that the ocean has been expanding, right? And so that reflects as sea level rise. The blue line is another independent measure, and this is a measure of the mass of the ocean, and it's measured from a satellite called GRACE. It's actually a pair of satellites that chase each other around the planet, and as they get deflected around, they'll see differences in gravity on our planet, and over time, they can see how gravity, that is mass, is redistributed on our planet. And what they have shown in that blue line is that the mass of the ocean has been increasing. Doesn't mean that water is being created, it means that water is being taken from land and being put in the ocean. A big contribution to that is melting land ice and melting snow. Some of that is groundwater pumping. The sum of the red and the blue is the purple. A completely independent estimate of the sea level. We've closed the sea level budget of our planet. We know why sea level is rising. It's because we're melting ice. It's because the oceans are warming. All right? And this is going to continue. So although we don't know what hurricanes are going to do over the 21st century, we are very confident that the atmosphere is going to be more moist and that sea levels are going to be higher. And so unless we have a very good reason to think that hurricanes are going to become less intense or less frequent, our risk for saltwater and freshwater flooding from hurricanes will increase. And that's the takeaway. So the first point, it's premature to conclude that we've seen a change to hurricane frequency or intensity from increasing greenhouse gases. We don't know what CO2 is going to do to hurricane frequency. We don't. And we don't know how hurricane frequency has changed, nor its intensity, at least over the long haul. So we can't say whether CO2 has done what we've seen because we don't know what we've seen and we don't know what we expect it to do. Okay? However, models allow us to estimate the sensitivity of hurricanes to global warming and to other factors. I didn't spend much on this, but over the next few decades, internal variability, the natural wiggles of the climate system, are likely to be dominant. So we're likely to go through phases where the Atlantic is active and the phases of the Atlantic is inactive, right? So just because we're inactive for a while doesn't mean that you should sell your hurricane shutters, right? Non-greenhouse gases, aerosols, are going to also be a big contributor. Remember I told you that the pattern of ocean temperature changes matter? These aerosols, they tend to be concentrated in certain places. It's a great way to make one place warm relative to another, is to shade only part of it. And on the century scale, North Atlantic response, maybe fewer storms, probably stronger, who knows? And I'm going to skip that fourth one, but I think when we're thinking about the risk, just because we don't know what hurricane frequency and intensity is going to do, doesn't mean we don't know anything. We know a great deal. We know, number one, that wealth population is moving to the coasts. And all the demographic projections that I've seen have it continue doing that. So from the risk being hazard times exposure times vulnerability, we're increasing the exposure. What we do about the vulnerability, that's a decision we need to take. That is how we harden or not against potential threats. From the hazard point of view, yes, the winds from the hurricanes are one of the hazards, but there's other hazards that are also very relevant. Particularly inland, the rain from storms is very relevant. Irene flooded all the way up into Vermont, right? From the point of view of coastal flooding, the saltwater flooding from the storm surge is also relevant. Both of those we expect, for very simple reasons, to become more of a threat as we go forward. So I guess I'll leave on that bright note that even though we don't know what hurricanes are going to do, we're pretty sure that they're going to be somewhat more threatening going forward. Thanks a lot.
Questions?
What modes of natural climate variability do you look at, and which have the most impact on hurricane precipitation?
So the question is, which modes of climate variability did we look at and which have the most impact? So we've looked at a number, and the community looks at a number. The El Nino Southern Oscillation, El Nino, is one of the most prominent modes. It tends to have a 5 to 7 year repeat. They tend to come and go every 5 to 7 years. Although you'll have epochs when they're more active and less active. El Nino events tend to decrease hurricane frequency. La Nina events, their opposite, tend to increase hurricane frequency. On the decadal time scale, there's a phenomenon that's known as the Atlantic Multi-Decadal Oscillation, the AMO, which it's not clear it's an oscillation, that it has a preferred multi-decadal time scale, or that it's confined to the Atlantic, but that's its name. And we think, so one of the bits of thinking is that the ocean moves heat northward across the Atlantic by taking warm water to the north, making it cold and dense, having it sink, and bringing that south, and that moves energy northward. That circulation, we think, sometimes accelerates and sometimes weakens. As it accelerates, you bring more heat into the North Atlantic, and that may give you more hurricane activity. We think there's a time scale of about 50 years on that it'll repeat in 50-year cycles. If you look at some sediment data from Iceland and from Bermuda, you see that. However, there is some indication that at least the latest cycle was in part driven, if not, some people say in totality driven, by pollution coming from Europe and North America and some dust, where in the post-World War II era, there was a lot of buildup of pollution over the Atlantic that shaded the Atlantic, decreased hurricane activity, clean air measures since then have removed the veil and so have warmed the Atlantic and increased hurricane activity. So that is one alternative explanation, that it's not a cycle, but that it's forced. So those are the main modes of variability. And then there's just plain old weather. If you're thinking about one storm, a particular location in space, weather, just randomness, may be one of the biggest determinants. I go back to Irma. Irma, there are a number of parallel universes to ours in which Irma caused devastation in Tampa because it was 30 miles to the left. And so the fact that Irma didn't smush Tampa shouldn't make us feel any more confident about the stability of Tampa. Any other questions?
I'm wondering if you can maybe elaborate on your last point about how like populations are moving towards coasts, and just talk to, now that this research is out there, like what implications does it have on maybe planning or development moving forward?
All right, so that's a great question. Why are people moving to the coast? Well, there's an aesthetic, at least in certain cultures, an aesthetic preference to be near the coast. People like. And in the United States, coastal properties are quite valuable and prestigious. So people of wealth want to move near the coast, or people want to save up for a lifetime and move near the coast. And so that's just sort of the trajectory that there's been. A lot of the commercial and high-tech sectors, if you look at the growth of sort of industry in the East Coast, for example, a lot of it has been New York, a lot of it has been Boston, DC. Those are all areas that are susceptible to hurricane activity, right? If you go on the barrier islands in North Carolina, just see the houses that are there, or up and down the Jersey Shore. It's crazy, right? And so that's one of these things. We just keep putting more and more things in places that we know hurricanes have hit. What are the policy implications? I don't know what the policy implications are, because the policy is a reflection not just of what the natural system is, but also what our values, our economic imperatives are. You know, we in this country, for example, we value liberty a lot. And I think that's 99% of the time, that's the right thing. We value property rights. I think that's also the right thing. And so there's a tendency to shy away from telling people what they can and cannot do in their own property. And I think for good reason. But we need to trade those off against other factors, right? And so this is more than just a discussion about the weather and the climate. This is a discussion about values, about economics, about what we want to do. And so the climate scientists and the weather scientists in the world are players in that conversation, but we're not the only parts that have to come in. What I would say is that all of us, if not now, later, you will be paying taxes, and you're paying taxes into the National Flood Insurance Program. The National Flood Insurance Program was created to support flood insurance in places that, you know, where people wouldn't write insurance. And it did it at a subsidized rate, and the way it does is it distributes it around everywhere. The flood insurance program is in the red. It's going to be in the red if there are no floods for quite a long time in the future. There are floods. And so how do you deal with this? This risk transfer mechanism is not necessarily working well. And I think it's going to become more and more of a stressor. Hopefully it'll still be able to pay out to the people that are damaged, that are expecting it, but it's not going to be able to do that indefinitely, I don't think.
Another question?
In front, over here.
I have a very simple question related to the first one. So if the interannual variability is going to be the dominant factor in the next decades, because if we look at the Atlantic sea surface temperature relative to the tropical mean, then there is not much trend. So that means the warming trend is actually like in parallel. But if there is any like shift between the interannual variability between the Atlantic temperature and the Pacific, so is that going to impact hurricane activity or frequency?
I think there will be, so if you have localized warming or cooling, it will impact Atlantic hurricane activity. The internal variability occurs for a number of mechanisms and a number of time scales. So we've seen internal variability as a big player in the past. And we have no reason to think it's going to go away. El Nino is not going anywhere. So it should be a player going forward. One of the things that I think, and I don't know how this ended up in the supplementary because it's one of my favorite slides, is we can learn a lot. So I've talked a lot about the last 100 years, 150 years. I think we can learn a lot by looking deeper in time. So the top left plot is a time series moving back in time. The year 0 is more or less present day, so that's the rightmost point. And 4,500 is 4,500 years before the present, so 2,500 years before the Common Era. What that is a trace of hurricane activity inferred from sediments in this little box over here. You see it on the bottom left. It's in the panhandle of Florida. It's a place called Mullet Pond. It's a freshwater, brackish freshwater pond that is separated from the Gulf of Mexico by a dune. And what you can see is that sort of riverine sediment sort of deposits most of the time. But every now and again, when you do a core, you will see these bands of coarse marine sediment laid down. And those are interpreted as hurricanes having come by and sort of overwashed the dunes and deposited. Well, what do you see? For the past 500 years in Mullet Pond, it's been relatively inactive. You see that trace is down at the bottom? Past 500 years is the entirety of European colonization and sort of culture in North America. There's been low activity. Right before that, that thing shoots up for another 500,000 years, right? From the 500 years before the present, so the year 1500, to 1500 years before the present, so the year 500 of the Common Era. You have much more activity than now. Then it drops down again, and then it spikes back up around 2,500 years before the present, or 500 years before the Common Era, into the past. There's no big changes to radiation, ice ages, or Eocene thermal maxima, or anything like that going on there. That's all within the late Holocene. That is all within one climate region. It seems that nature can throw a lot of very different things at us. And a question I have for myself, we don't understand this record. And if we were going into one of these active phases, would we know it? Could we recognize it? How far in would we be before we realized that we were in a 500-year active hurricane season? Right? And because that would have a lot of repercussions. So in addition to whatever we do to mess around with the system has a way of messing around with us too.